Alright, so today we'll be continuing our study of vectors, and specifically we'll be going over the last and probably the hardest topic from the vectors unit, and that is projectile motion. And then that is because projectile motion combines a lot of the stuff you've already learned, as well as some stuff that'll be new, and particularly if you're not doing physics, can be quite challenging to understand initially. So let's start by defining projectile. Projectile is any object that is projected up, thrown or fired, and falls down under the acceleration due to gravity, neglecting air resistance. Projectile motion describes the path of the projectile using as a point, usually as a point moving on the Cartesian plane. So essentially, if we can represent a projectile as an arc, as all projectiles move in parabolic motion when only under the influence of gravity, it'll go through as an arc, and it'll slowly come down, and it'll have a peak, which will be its maximum height. It'll have a range, which is its maximum x displacement, and it'll have a time of flight, which is the amount of time it takes for it to fall. Now, we can represent this using vectors. So, and that's basically what we'll be doing. But when you're using vectors for projectile motion, it's important that you realize that the x components of the vectors, so the horizontal components and the vertical components, are completely independent of each other except when involving time. So essentially, your velocity, your acceleration, and your displacement in your x direction has absolutely no impact on the vertical direction. The only thing that connects the vertical motion and the horizontal motion will be your time component. Otherwise, we're going to be treating the horizontal and vertical motion completely independently when we're working through these examples. And those of you that have studied physics, this will be rather familiar, although you aren't able to use the formulas that you've probably grown so used to when doing physics. So the initial velocity vector of a projectile is given by this, where this is an I and a j component, and we have our angle theta of projection, so the angle at which it's thrown or projected, and the v is the initial velocity. So this will be the initial velocity as you throw it, and this is the angle, so this will give you your initial x, and this will give you your initial y, and we can use the vector components to represent this. And so we also have an acceleration vector of a projectile. So this just shows the only thing causing acceleration, meaning the only force acting on the object, is gravity, as it's negative g. So essentially gravity is acting down in the vertical component. So it's forcing your object down as it goes. As you initially project it up, it forces it down, and that's why it falls again. And g usually takes a value of 9.8 meters per second, or alternatively, it'll round it up to 10. And so if we integrate our velocity, our acceleration component, and we use our initial velocity, then we can actually derive this expression for the velocity vector of a projectile. So if you wanted to find the velocity, you could use this. And moving on, if we then integrate that again and use our initial conditions, we can develop the displacement vector. And this should all be familiar in terms of being able to integrate and differentiate your accelerations, velocities, and displacements to get one another. However, it is really important to know that usually in physics and in your previous studies, you would have just used these formulas directly, and you would have just gone straight into, oh, I want the displacement, I will just use this formula. Importantly, with mathematics, specifically with this topic, they want you to show where these come from. So the only things you're really allowed to take for granted is the initial velocity. You're allowed to use that, that's a given formula, and the initial acceleration. You cannot use the velocity and the displacement vectors. You will have to derive those in each and every question you do for the specific question you're doing. But still important to look at the general formulas, so that way you know if you're doing it correctly. And I'll show you how to integrate and to get these formulas in the question that we're going to do. So looking at the question, Marlin stands on a cliff 35 meters high and throws a stone into the water with a velocity of 16 meters per second at an angle of 30 degrees to the horizontal, find the vector for the stone's displacement in the form S is equal to AI plus BJ given G equals to 10 meters per second. So what's happening in our scenario? So we have no marlin, so let's just say no marlins up here, label as N, and they are throwing a rock off the cliff, and it's going into the water, and it's initially at 30 degrees, and it is falling a total height of 35 meters. So from here, we're going to use those same initial conditions, and we're going to build up an expression for what we want. All right, let's go ahead and do that. So I'll leave this up here so we can work through it. So we start with our acceleration. We know that the initial acceleration is just given by gravity. And now, in all of these examples, you have to integrate and get each component, and then you have to solve. Because those formulas that we saw earlier don't always work in every situation. They're just a generalized formula for the majority of situations you get yourself into, and they should always look similar to that, if not the same. So now we integrate to get our velocity, because we want our displacement. So now we have to integrate to get velocity, so we can then integrate to get displacement after. So if I find my velocity is equal to the integral of my acceleration with respect to time, and then this is going to be the integral of minus gj with respect to time, and this is just going to be equal to, you just integrate this normally, so this just becomes minus gt, and the j you just treat as a constant, doesn't really do anything. So we get a j component, but because this is an indefinite integral, we've got a plus the c. So from here, and also note that I'm leaving this in terms of g. I haven't replaced this with 10, as I will only substitute my values at the end after I've done everything. That way, I don't have to worry about carrying numbers through, and I can keep track of what things actually are. For example, since this is g, I know that it's the gravitational constant. Anyway, so now in order to find c, we have to use the initial conditions for velocity using the initial velocity. So this implies that v is equal to v cos theta I plus v sine theta j minus g0j plus c. Sorry, that is not quite correct. That should be equals to minus g times 0 j plus c. So essentially, this g component just disappears. Also, that should not be a vector. And so c is just equal to your initial velocity, and that will always be the case. And so this implies that b is equal to minus j t minus g take g plus b cos theta I plus v sine theta j. And so now from here we can collect our j terms, and we can simplify this to look a little bit nicer. V cos theta I plus v sine theta in brackets minus gtj outside the brackets. All right, and so from here we're just going to integrate this again to get our displacement. So then we use that displacement is equal to the integral of our velocity with respect to time. And so then this is just going to become vt cos theta, because again I'm just going to integrate these components separately. Vt cos theta I plus v sine theta, vt sine theta in brackets minus gt squared over 2. I'll just actually clear this up a bit, make sure the t is apparent. t sine theta. And this is a j component. All right, now, is that everything? It looks like everything, but if you look, it's an indefinite interval, so we've got plus c. And this one's relatively simple, so we're just going to use initial conditions using initial conditions. So we could say that this is initially at 0, and so it's got to go down to minus 35. But I will call the bottom of the cliff 0, so I will say that this is positive 35, simply because that's the way I prefer. I prefer that the lowest point is 0, so we're not dealing with negative displacement. So this implies that the initial displacement is equal to 35 meters, which is then equal to, and these three terms, are going to disappear because they've all involved t because we integrated. So that's just going to be equal to c. So our c is 35. And so now I'm just going to continue the working over here because we have to just essentially separate those into the given variables. Actually, also, that's not 35, that is 35j, because it's 35 in the j direction. So we get the initial displacement is equal to bt cos theta I, and then I'm just going to essentially include this 35j into this, plus bt sine theta minus gt squared over 2 plus 35j. So this is our displacement vector. What is the last thing we have to do? We have to substitute in. So now substituting in, we just get 16 root 3 over 2, because t cos 30 is root 3 over 2, t I plus 16 times 1 over root 2, because, sorry, that should be 1 over 2, not root 2. 1 over 2, because sine 30 is 1 over 2, t minus 10 over 2t squared plus 35j. And that's because g was 10 from the given question. So now, just going through and simplifying this a little bit more, we get 8 root 3 t I plus, and this is going to be 8t minus 5t squared plus 35j. All right. So that is our final solution to part A, and we are done. Well, at least for part A, because we have now found our displacement vector in terms of our I components, our horizontal components, and our j components. And notice how throughout I always kept those two components separate, but I joined the j components and the I components as I could, but I never put both I and j together. I just kept them separate. But I pulled in the 35, the 5t squared, and the 8t all together. All right, so now we are going to use this. So I'll just rewrite this up here. Equals to 8 root 3 t I plus 8t minus 5t squared plus 35j. All right. Let's just erase all of this. And the second component, let's redraw that cliff in a moment. The second component of this question wanted us to find the time it took for the stone to hit the water. So essentially, how long until the stone was in the water can be found using the j component. And I'll go over how we do that in just a moment. So this is called the time of flight, and it's the time that your projectile spends in the air. And so if we look at the example we had with the cliff, in this one, it'll be the time between when she throws it, it goes up, up, down, and then it goes into the water. And that's our time of flight. So essentially, since down here is 35 high, if we're on a scale, the bottom of the cliff would be 0. So that means that we want to find the t when our j component of our displacement is 0. And that's essentially how you find time of flight. So when you want to find time of flight, you want to let your horizontal, from your displacement, you want to let your vertical component be 0, and then you rearrange and solve for a time. Now you should always get 2 times in these examples, because the projectile motion is parabolic, so you expect to get 2 times. Let's go through that. So we want our j component to be 0. So we want 8t, so we want to let 8t minus 5t squared plus 35 equal to 0. So I'm just going to multiply everything by -1 to get rid of that negative on the t squared. So we get 5t squared minus 8t plus 35 equals to 0. So now from here we use the quadratic formula. So using the quadratic formula, we want to then have t is equal to minus b squared, so that's going to be actually plus 8 plus or minus square root of b squared, so minus 8 squared minus 4 times a, which is 5, times c, which is 35, or so that should be 5, all over 2 times a, and a is 5. All right, so now we can start putting this into our calculator. So we get 8 plus or minus square root of, and this is going to be 64 minus 4 times 5 times 35, and that's going to give us minus 636. I'll just make sure I did that correctly. 64 minus 4 times, that's the issue. This should be a minus 35. Minus 35 times 5 times minus 35. That's going to actually give us 9. It's a much nicer answer. So this is going to be 9 all over 10. And then that is going to give us 8 plus or minus 3 all over 10. And so from here, we're going to get 2 solutions, and they're going to be in the plus case and the minus case. So in the plus case, we get 8 plus 3, which is 11 over 10. And in the minus case, we get 8 minus 3, which is 5 over 10, or a half. So now how do we know which one's which? Well, in parabolic motion, we should get an example coming down here at this time. And so we would want the second case in all of these scenarios, because we don't want the initial one, which is sometimes going to be 0 and sometimes going to be negative, or in this case, it's actually positive. But it doesn't matter as much as what we really want to see is we want to see this example of it going up and then landing the second time. That is the final time that's going to land. So we want the bigger one. So we want the 11 over 10, or 1.1. So we want t is equal to 1.1 seconds. And that is going to be our solution. Yep. And that's it. And so we found the time of flight. It's 1.1 seconds for this projectile from her throwing it to it landing into the water. So now the last part of this question wanted us to find the horizontal range, the distance from the cliff that the stone is once it hits the water. And so the way we're going to find that is we're going to use the time of flight, And since we want a displacement, we want to find how far it is away from something. We're going to use the displacement formula. And specifically, we want to know how far away it is from the cliff in the horizontal direction, because he's throwing it from the edge of the cliff. So the horizontal component is going to give us our distance. So we're essentially just going to substitute this time into our horizontal component, and we are going to get that the displacement is equal to 8 root 3 times 11 over 10 I. So I've just subbed in my t to that, and then this is going to give 88 over 10 root 3 I, which simplifies down to 44 over 5 root 3 I. And then we're done. So we found 3 components in this question. We went all the way through and we found the displacement formula. We then used the vertical component of this displacement formula to find our time of flight. And then we use that time of flight to then find our horizontal displacement, or our maximum range is another word for it. And you'll see that come up quite a bit. So this is actually a pretty archetypal question for projectile motion, and then you have to find multiple components. You have to derive formulas from the projectile motion method, whether it be your velocity or your displacement coming from your acceleration. And from there, what you have to do is you have to solve different characteristics. So usually it's the range, which is going to be given by your time of flight on your horizontal component, or it's going to be your time of flight, which is given by your vertical component when that is equal to 0 when it hits the ground. Or you might be asked to find the maximum vertical height. And the way we find the maximum vertical height is we go back to the acceleration question, and we want the vertical component, back to the velocity, not the acceleration, and we want the vertical component of the velocity to be 0. And that's because as the projectile goes up, 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 the velocity will be big, and then it'll slowly decrease until a point where it starts to go down and starts to fall in the opposite direction. So there's a split second in the very middle, at the very peak of that curve, where the velocity in the vertical direction is 0. And so that's how we find our maximum height. We find the time at this point, and then we substitute it into the vertical component of our displacement. So just a little bit of a summary of what I just mentioned. So the speed of the projectile is the speed of the projectile at time t, is the magnitude of the velocity vector at that time. So if you want to find the speed at a specific time, you get the velocity vector and you find its magnitude, and then you substitute in that time. The maximum height of the projectile. The maximum height occurs when the y component of the velocity vector is 0, and is the y component of the displacement vector at that time. And then when we find the time of flight, it's the end of the flight is when the projectile lands on the ground. So the time of flight is when the y component of the displacement is 0, which is exactly what we just found. And then when we want the range of flight, the horizontal range is how far the projectile reaches when it lands, and it's the x component of the displacement at that time. So it's the x component of the displacement at the time of flight. So just remember, when you're doing projectile motion questions, that these are the 4 components that you'll generally be looking for. But when you're determining your displacement or your velocity vectors, you have to start at the initial acceleration, and you have to substitute through and go all the way through the question to get your answer. You can't just use the formulas as you saw in our example. We had that positive 35, so our displacement vector was a little bit different than the formula given, but it's still important to know about the formulas, just to know if you're on the right track. Because if it looks vastly different to the formulas, then there's probably something wrong. I hope that this lesson was helpful, and I'll see you guys next time.